Hello everyone, and welcome back to Head in the Clouds. Today we've got something special for you, a deep dive into Docker commands that will boost your container efficiency. We're drawing inspiration from our recent Medium blog post, which has been a massive hit. If you haven't checked it out yet, the link is in the description below. So let's start with the basic command to really get started with Docker. So we'll be covering the Docker pull command. This command is used to retrieve images from a registry and make them available for use in a containerized project. So let's go to Docker Hub and search for an image, let's say Ubuntu 2004. So if we go to hub.docker.com and click on the Explore button, in here we'll be able to search for Ubuntu. If you click on the top one, over here we'll be able to see all the supported tags and respective Dockerfile links to each one of them, and more information, of course, about the Ubuntu image itself. So to retrieve an image from Docker Hub or any registry, we'll have to provide its name and tag. So that would be Ubuntu 20.04. So let's go back to our terminal, and here we'll type docker pull ubuntu and then 20.04. This will start pulling, of course, the image from the library itself, and it will ensure that the specific version is downloaded that we need, or perhaps if we tag it or specify to be the latest one, then we will download the most recent one. So this is an example of Docker 20.04, and if we do Docker images, we'll be able to see the Ubuntu image with the tag 20.04 in our repository. If we would like to have the latest version, we can do that by running the same command, docker pull ubuntu, and then specify latest, which will give us the most recent or up-to-date version of Ubuntu. And if we do Docker images one more time, we'll be able to see two images now listed in our repository, which will be Ubuntu latest and 20.04. As you can see, Docker images are versioned, and each version has a unique tag. And by specifying the image tag and the image name, you can ensure that you're using the correct image and the version in your Docker environment. So it's always advisable to check the image name and the tag before pulling it in order to avoid errors and unexpected results. Moving forward to listing images, once we've downloaded an image, we would like to be able to see what exactly we have downloaded so far. And as we've seen, to be able to do this, you can use Docker images command, which will give you a summary of all the images saved on your computer. So if we clear up the screen and do one more time Docker images, this is the latest objective that we have, an overview of our repository to this very moment. Of course, this command allows you to see a list of all the Docker images that are currently available on our computer, including all the details relevant to us, such as the name of the image repository, its tag, and the unique image ID, which will be different for each of them. When you run the command docker run ubuntu with a specified image tag, The container exits it immediately because there is no persistent process running in the foreground. The container runs the default command specified in the Ubuntu image, which typically is something like bin bash. However, because there's no interactive terminal, the bin bash process completes and the container exits. So let's demonstrate the differences between the both. So we will run firstly docker run Ubuntu 2004. And if we do docker ps, we will see that there's no currently running container listed on our computer. And if we do docker psa, we can see that the container with a specific ID and the image we've specified exited 11 seconds ago. So in order to keep the container running, we can provide a command that would essentially run persistently. For example, we could run a simple command like tail-f dev null, which this command will not do anything in specific, but will keep the container alive. So it will continuously tail the content of dev null directory, which is essentially an empty file. So here is an example of that. If we do docker run -d, which will run the container in the detached mode, which means it will run in the background. And then we'll specify again the image with the correct tag. And then we will do a command tail-f dev null. And here we will also see the specific ID. So this is obviously the container ID that is printed out on our console. And this can also be used later to interact with the container if needed. So if we do docker ps, we'll be able to see that this container now is up and running for the past 24 seconds. We can also see its container ID relevant to the one above, and also the correct image with the tag that we've specified when we started the container. After running these commands, the first one will exit immediately, as we've seen, while the second one will remain running in the background. And this is a really helpful illustration to explain the importance of having a persistent process in order to keep a container alive. Now let's talk about creating your own images using Docker build, or famously known as Dockerising your application. Docker build is a command that helps you create customized images for your application. It uses a configuration file called Dockerfile to generate an image that suits your application's specific requirements. You can specify various parameters, such as the base image which we would like to use, and all the dependencies to install, as well as other configurations for fine-tuning of the image to your application's needs. By creating your own images using Docker build, you can easily replicate and distribute your application across different environments while ensuring that it runs smoothly and consistently. Now, we will use Flask, a lightweight web framework, to create a simple web application in Python. After this, we will create a Docker image for our application. By building a Docker image, we can make sure that our Python web application runs smoothly across different platforms. For the purpose of this demo, we will use Visual Studio Code just so we can edits and create, of course, the necessary files whilst we're interacting with terminal. So we highly recommend you to download it if you haven't done it already and use it for these purposes. We'll start by creating a new folder for testing purposes, which we'll start by make dir command, and we'll say head in the clouds, Flask Docker demo. And if we list it, we can see the new folder in there. Ensure you're in the right location. And we will also create a new file using the touch command, and we'll call it app.py for our Flask application. And if we extend it here on the left-hand side, our freshly created folder, we'll be able to see the app.py file in there. You can also see that with Visual Studio Code, you have different extensions, and it's automatically picking up that this is going to be a Python file that we'll be working with. And we'll start by specifying in our code to import the Flask class from the Flask module. So we can do that by typing from Flask import Flask. And next we will create a Flask app instance. So that will be an instance of the Flask class that we'll create and assign it to a variable app. So let's do app equals Flask and then name. The next one, we will define root and handler function. So the app root decorator associates the URL path with the, let's say, hello function that will name it specifically. And when a user basically accesses the root URL, the hello function will be called. So in order to do that, we will type app root, and then in brackets, we will do just the / for the root URL. And then we will do next row definition of our function, which will be def hello with brackets. And we will put a return, let's say hello, head in the clouds. This is Docker with Python. And lastly, the handler function. So the hello function is a simple handler, of course, that returns the string, which will be hello, head in the clouds. This is Docker with Python as response. And to be able to run our application, the conditional statement will have to be added in here, which will be if name is equals to main. We will then do app.run. And then we'll set debug equals to true, host, which will be 0.0.0.0. And essentially, this will ensure that the development web server is only started if the script is executed directly, so not when imported as a module. The app.run method starts the Flask development server. So here it will run the server in a debug mode, as we've defined it, set it to true, and also binds it to all available network interfaces, which we specify in this case to be host 0.0.0.0. And with this Flask application, we can build a Docker container that pretty much encapsulates the application and its dependencies. The application will be accessible via web browser at the root URL, which will be HTTP localhost and then the port number by default when the Docker container is running. Now we will create a file in the same folder. So head in the clouds, Flask, Docker demo, and we will name it requirements.txt, which will appear just over here on the left-hand side. In the same working directory. And if we click on that requirements.txt, we can see that at the moment that file is completely blank. This will essentially be a list of all the dependencies required for our project. So in order to add the dependencies to this file, we can do this in two ways. Firstly, we can type something like pip freeze and then greater than symbol requirements .txt file, which will essentially allow us to use this file to install all the required dependencies on other machine, or we're setting up a new Python environments for our project. So let's see what happens when we execute this. So if we just minimize this a little bit so we can extend the requirements.txt file, we can see a list of all the dependencies currently installed in our Python environment, which got directly written or imported into the requirements.txt file itself. There's pros and cons to this approach. Of course, the good side is that we can capture the exact versions for reproducible environments, and we can also clearly list all the dependencies and their versions. However, inclusion of unnecessary packages may include not directly required packages in our application. So just to be, aware of that. The second approach is, of course, to manually specify dependencies in the requirements.txt file. Pros with this is, of course, explicitly being able to specify only needed packages for this particular use case, and of course the simplicity, so the cleaner and easier way to manage the requirements.txt file. The downside, of course, is the maintenance, so it will require a manual tracking of updates and version changes. So just be aware of that and look out for it. Okay, so the next step will be to create a Docker container for our Python application. And in order to do that, we will have to follow a few steps. So the first one is to create a Docker file. So we'll do touch Dockerfile, which will appear on the left-hand side. Again, you can see that it's specifying the type, the Visual Studio Code. It's selecting the right language mode. And essentially, as we already mentioned before, this is a document that will contain all the instructions needed to build our Docker image. So we will make sure that this Docker file is saved in the same directory as our Python application files. So moving on, the Docker should specify the base image that we would like to use and any additional dependencies that we might want to have installed as part of this process. So the commands required to start our application. So let's start by defining our Docker file. So as we said, we will use an official Python runtime as a parent image. So in order to specify that, we'll type in our Docker file from Python, and then we will specify version 3.9. And then we will set the working directory in the container to be user source app. And we will also like to copy the requirements file that we've created earlier into the container at user source app file path or direction of our directory, sorry. So that will be copy, and then we will type requirements.txt and then // as our working directory is already set to that file path. So there's no need to specify that, but just // is a local kind of allocation of the required or the files that we want to copy across to that specific directory. And now we will ensure that all the necessary packages specified in the requirements.txt files are installed. So we will do run pip install, and then we'll specify no cache dir -r requirements.txt. We will then copy the current directory contents, so everything that we can see here on the left-hand side, into the container at the same file path that we've set previously of our working directory. So we'll do copy ... We would also like to expose the port on which the application will run. So let's do expose 5000. And lastly, we will define the command to run our application. So cmd, and we'll do square brackets Python, and we will run our app.py, which is for Python, our Python file. So we'll specify the commands to execute that application. Once the Dockerfile is set up correctly, we will use it to build our Docker image and, of course, start our application inside the container. Great. Now that we're happy with our Dockerfile, let's go back to our Visual Studio Code and navigate to the directory to ensure we are containing our Docker file, which we can see it just here that we worked through earlier. We also can see our app.py application in here, and the requirements.txt file. For the simplicity of this demo purposes, we've just decided to include the minimal kind of requirements for our dependencies at the moment to avoid any confusions or errors, perhaps with some other dependencies. So ensure that is also replicated on your end. And if we're happy with that, let's start by typing the following command, which is docker build and then -t. We can call this Docker image head in the clouds -python -app, and then let's say give it a version 1.0. We'll also put a dot in here to ensure that it's including all the relevant and needed files to start the process of building the Docker image. That went pretty quickly, as the simplicity of the application and the dependencies files is pretty straightforward and short. So we can see the building process started 1.1 seconds it lasted in total. We can see the steps they took to go through, the current status, which is showing finished, and some more information, of course, on what exactly has been executed as part of the building process. And if we do Docker images to list all images that we currently have on our local machine in the repository, we can see our newly created image 3 minutes ago, which is called Head in the Clouds -Python -app with a tag version of 1.0, its own image ID, and obviously the size. You can also see it here. It's occupying at the moment 1.01 gigabytes. Now that we're happy with our Docker file, let's carry on with running the Docker container using the previously created image. So we'll kick off by demonstrating the access to our Flask application inside the Docker container. And for this purpose, we will use, we'll do this directly on the port 5000, as we specified it earlier in our Docker file, where when we expose the port on 5000. So you can do this by running directly the following Docker command. So we will go back to our terminal, and we will firstly check if there are any currently running containers, just so there's no conflict in running the new ones. And once we're happy with that, we will type docker run with specific port on 8080, which will be mapping the port 8080 to our host machine. And then we will specify port number 5000, which will be the port in the Docker container, allowing, of course, the access to the application on both ports. And lastly, we will specify the Docker image that we've created previously. So that will be Head in the Clouds Python -app, and then version 1.0. Now you can see the actual Flask application running. And for the next steps, I would like to use curl to demonstrate accessing the application on both of the mentioned ports. So they'll be on 8080 and 5000. And we will open two separate terminal windows to run the following commands. So we will leave this one running for the testing purposes, and I will try to get a little bit more room in here, and then I will open a separate terminal window to access the application on port 8080 that is mapped to port 5000 in the containers. So whilst we have our application running here on the left hand side, we will do curl http, and then we will do localhost on port 8080. And we can see the return, hello, Head in the Clouds. This is Docker with Python. So this will show us the successful testing and the response coming directly from our Flask application. Now, to access the application directly on port 5000, this time inside the container, we would like to run curl for that, so directly inside of the other Docker container in order to access the Flask application running in the first container on port 5000. So we want to make sure that both of these containers are part of the same network. Additionally, we might want to ensure that the Flask application container is running and that is accessible. So here's an example workflow of that. Firstly, we will start by getting the container ID of the currently running Flask application. So You can either do Docker PS, of course, in here you'll be able to see the container ID. However, for running the following commands, we would like to export it to retrieve the container ID and save it in a variable. Let's say we can call it Flask container ID, which will be equal to this following command, Docker PS -qf, and then we will retrieve the image that is currently using our Flask application. Apologies for a typo. And now we'll run another command which will run curl inside of another Docker container. So basically we'll spin up a second Docker container which will run purely just a curl command to retrieve the information as we saw previously on port 8080. This time we will do it by calling the local host 5000 directly on our Flask application. So to do that, we'll run docker run and we'll specify a network, which will be container, and then we will use the previously created variable. So that'll be Flask container ID. And then we'll use an image, which is just called curl images, latest version. And then we will lastly specify the command that we want to run. So that will be HTTP localhost on port 5000. And in here, just to see the response that we got. So let me just extend a little bit more. Hello, head in the clouds. This is Docker with Python. The message is not being displayed really well, but we can also see the 200 response here as well in our currently running Flask application, that this has been, of course, successful. So if you do encounter any issues, please make sure that both containers are running and that the Flask application container is accessible on port 5000. Additionally, you could also make sure that the curl images container has access to the network namespace, as we've specified previously, of the Flask application container. And both applications should retrieve the response from your Flask application, demonstrating the accessibility of the application on both ports. The reason why we did this in the real world scenarios, if you do need to do any additional service testings, let's say if you need to quickly test services in a containerized application by running commands from one container to another to check their functionalities. And of course, for network troubleshooting, any sort of networking issues that you might come across, it's great to, of course, troubleshoot container issues using utility containers with tools such as curl or ping, as we've just demonstrated now for rapid diagnostics. Lastly, we would like to, of course, see all of this happening in our browser as well. So the best way to test that is by going to any of your browsers on your local machine and by typing HTTP localhost 8080. And in here, if I just zoom that in, we'll be able to see, hello, head in the clouds. This is Docker with Python. So once you have followed these steps, you will see that we have successfully created a Docker image of our Python application, Python Flask application itself, and that the image that we've created will contain our Python application and all its dependencies, making it really easy to distribute and run consistently if you do need to repeat, of course, these steps across various environments. Before removing an image, it's important to check if any running containers depend on it. If we are using container, like in this case, it's still live, so removing an image will cause certain issues or errors, or even crash the container itself. So let's try to demonstrate this live whilst we have this Flask application running here on the left hand side. So if we do Docker images, we'll be able to see the image that we are currently using inside of this container, which will be head in a clouds Python app version 1. And if we run the following command, which will be docker rmi for removing images, and then specifying head in the clouds Python app version 1, we'll see this error response from Damon indicating a conflict, being unable to remove repository image head in the clouds Python app version 1, and that it has to be forced that the specific container is currently using it. So that'll be 2bf4e, and if we do docker ps, we can see that is being allocated obviously to the same container ID that we can see here being referenced in the above error. So to avoid this, we should really check firstly if there are any containers running or that are currently using the image that we are intending to remove, and if so, we would first stop and remove any of the existing containers before deleting the image by running the following commands. So let's stop this application for a minute. We'll clear this terminal window on the right hand side, and we'll run docker ps to check if there are any currently running containers, because we've just stopped our Flask application on the left hand side. We can see currently this area being completely blank. And if we do docker ps a, which will list all of our containers, including the stop ones, we'll be able to see previously the curl container that we use for testing purposes, and of course the other container that we currently have that we've just stopped, which was the Flask application itself. So to be able to remove the image, we will run again Docker images to get the container, the image ID, and we will run docker rmi for removing images, and then copying the image ID and pasting it in here. Okay, so it's still assigned to the Docker container, so let's just try to forcefully remove it by running this command and copying the container ID, which is here. That confirmation ID underneath the command we just ran is indicating that it has been removed. So if I clear up this screen, we should just be able to see the curl container that's been previously stopped. And if we go and do Docker images again, and then docker rmi with the specified image ID, we can see that it's been untagged and successfully deleted. So Docker images, we don't have currently listed the head in the clouds one, as we've managed to successfully demonstrate its deletion process. So this is really, really handy and something to use for best practices, of course, in reality, as it frees up quite a bit of disk space on our system and ensures that the system remains stable and functional. Lastly, we would like to demonstrate the container lifecycle. So what exactly does it mean for us to run and manage our applications? So to get started with these tasks, let's run a container. So we'll begin by firstly just tidying up our workspace here a little bit and clearing the previously run commands to have a little bit more visibility on our screen. And we will recreate the previously deleted head in the clouds Python app Docker image. So we'll just rerun the following commands. So that'll be Docker build, and then we will specify head in the clouds Python app 1.0. Also, we'll use a dot to specify to use the currently existing files in here that we used, of course, for this creation of the application. So just make sure you're in the correct directory. And if we run that, oh, sorry, there's a typo. It's Docker build T. And we'll see the building process has started, and it went through all the setup required to build the image, and it has been completed successfully. So if we clear our screen and do Docker images, once again, we'll be able to see the head in the clouds Python app image in our repository with the right tag and this time different image ID. And we can see also the size remains the same as we haven't modified or added any other dependencies to our application. So let's clear up the screen again. And when we've just demonstrated, when we run a container, there are a few things that we'll need to specify for creating the following Docker container. So firstly, you'll need to decide if you want the container to run in the background or not to be using the detached mode. So that will be just an additional -d. You also need to map the correct ports so that the container can communicate with your computer. So giving the container a name is really important too. So for best practices, it's good to utilize it in your daily basis, as that makes it easier to manage and identify the containers you're working with. And finally, you must specify the image, as it determines what software and dependencies will be included in that container. So let's move on with the next command that we will go through in this video. So that will be Docker run, and for this testing purposes, I'll use the detached mode. So I would like to prefer it to have it running in the background, and also specifying the port 8080 and then 5000, and we'll give it a name, head in the clouds Python app, and which will be, of course, the name of our container. And also we need to specify the Python image, which will be the known image with its image tag. We can see, of course, the container ID, just confirmation that it has been successfully created. So we can see it here running for the past 7 seconds with the container ID matching the above, also using the correct image as we specified in our command, which is executing this Python app.py for Python. And also we can see the ports being allocated, the host port and the container 8080 and 5000. And of course, this is the name lastly specified in this overview. And when the container is running, you can see the curl command inside it to get a response from the desired endpoint. So curl is a really, really useful command line tool that helps us transfer data from or to a specific server. So it supports various protocols such as HTTP, FTP, SCP, and so on. By running the curl command inside the container, you can interact with the application running on that container and retrieve the response from the endpoint, something like this. So if we just want to ensure we get the correct container ID, we will run once again Docker PS. We'll retrieve the container ID from this command, and then we will run docker exec and then -it, paste in here the container ID, and then we will lastly run the curl command, which will get the HTTP local host 5000, and that will retrieve the response, the information we're looking for, which will be hello head in the clouds. This is Docker with Python. The Docker PS command helps us see what Docker containers are currently running on our system. You can view details such as container ID, names, status, ports, images, and so on. This command is very, very useful for managing and monitoring our Docker containers. And you can even filter and sort the output as and when you need it. So overall, Docker PS is a helpful tool for keeping track of your Docker containers. So let's clear up our screen and run a few commands for demonstrational purposes. So if we do Docker PS, we'll be able to see the currently running container that we've previously spin up. So that will be using the known head in the clouds Python app image. Now, moving forward, if you want to see a complete list of all containers, you can use the -a flag. As we've previously seen, we have been using this command quite frequently, and it will give you a detailed information about each container, again, going through the status, size, creation time, and so on. It is really helpful when troubleshooting issues or maintaining your containers. By using the Docker PS -a flag, you can have a full understanding of all your containers and make smart decisions about how to manage them moving on. So if we type Docker PS -a, we'll be able to see the currently running the existing container that we've started 9 minutes ago, and we can also see some other containers that are no longer active and that have exited some time ago, such as the curl container that we used previously for testing purposes. When you stop a container, a specifically running container, it's important to do it gracefully. This means giving the container enough time to exit it properly, which allows any processes inside the container to finish their tasks and save any important data. To do this, you can use the command docker stop with the option --time if needed to specify a time frame before forcefully terminating the terminal. So this simple practice will help you prevent data loss or even corruption, and is considered a best practice. So for this demonstration, we'll just use a simple docker stop command to stop our currently running Flask application. So that will be docker stop, and then we can copy the name of the application, which will be head in the clouds, Python app, and then we can see the confirmation of the name of the container. So if we do Docker PS, we will no longer see our Flask application running in there. So in order to check the full list of containers, both running and stop, you can once again run Docker PS-A to give you a full list of that. And here under status, we can see that both of these containers are now showing the exited status. If you need to restart a Docker container, you can do so by running the Docker command, which is docker restart, and the container name or ID. This will stop and then start the container again with the same settings and configuration. So let's start the stop container that we've just executed previously, the Docker stop command. So that will be the head in the clouds Python app. So let's type Docker restart, and then we will copy either the name or the container ID. And in here, we can see once again the confirmation that's been successfully executed. And if we do Docker PS, just to confirm it's up and running, you can always go back to this good old Docker PS command. Lastly, before removing a container, once again, I would like to really give importance to this, that we should firstly stop it before any kind of further procedures when it comes to the removal of the container itself. Removing a container can cause unexpected issues or even data loss. So it's really important to be careful with this. To release the resources being used by the container and avoid any further complications, stop the container before removing it. So this will ensure all the processes are terminated properly and that all your data is saved. So let's clear up our screen and we'll run Docker PS A. That will list all the currently running or exited containers. And let's move on with Docker stop, and then we'll copy the container name head in the clouds Python app. We can see the confirmation once again, and if we do Docker PS A, we can confirm the status is now exited 5 seconds ago. And if we do Docker images, we will see our Flask application in here, just highlighted in the repository. And we will then proceed with removing the Docker image. So that will be Docker remove, the Docker container. We will then proceed with Docker remove command to delete the Docker container, which we just stopped in here. And we can see again confirmation ID of the container that's been successfully executed. And if we do Docker PS, we can only see now in this list in the overview the previously exited curl container only, and not our Flask application. And lastly, as I've just started demonstrating, we would also like to, for housekeeping and ensuring that our system is tidy, we will also remove our Docker image that is no longer in use. So we can copy the image name or the ID and then run the Docker RMI command to untag the image and also delete it to save up some time, which is save up some space, which is around 1 gigabyte, which is quite a bit taking up from our system. So if we do Docker images, once again, we will no longer see it in this list. And that wraps up our Docker journey. We've covered pulling images, running containers, building custom images, and navigating the container lifecycle. Pretty much everything that you need for a solid foundation. In our next video, we'll be diving into a crucial topic, data persistence in Docker. Have you ever wondered how to keep your data intact when containers come and go? We've got all the answers. So don't forget to subscribe, hit that notification bell, and join us for our next Docker adventure. If you enjoyed today's content, give us a thumbs up, share your thoughts in the comments below, and check out our Medium blog post for an extra dose of Docker wisdom. Thanks for joining us today, and until next time, bye-bye.